Okay, so I think we can start. So we were talking about sampling based approaches for reliability analysis, and in sampling based approaches we have till now talked about two types of sampling. The first one is the Monte Carlo simulation, and the second one is the importance sampling, right? So to quickly recap, we have discussed two sampling schemes. Two sampling schemes. The first one is Monte Carlo simulation, MCS. And in MCS, how do you calculate probability of failure? The basic idea, you will basically perform experiments, count number of failure points, divide the number of failure by number of experiments, right? Mathematically, we write it as Pf hat is equal to 1 by n summation indicator function in the failure domain of x, and then the ith sample I equal to 1 to n. Again, previously I was writing xi in the subscript or suffix, but in books, as I told last time also, that when it is sample number, it is generally goes to the superscript, and it is generally inside a bracket, actually, to be more specific. When it is variable number, first variable, second variable, third variable, then it comes to subscript. Okay, so to be more consistent, I changed it in the last lecture, right? What is the problem with this? Slow convergence, right? Which means you need lots of sample, particularly when the failure probability is small, or what we want to call it as a rare event probability. Or for rare events, we will need lots of sample, right? So the caveat or the limitation is that slow convergence. Okay, and you are aware of that by now, right? The slow convergence fact, you are aware of that by now, right? What was the thumb rule in Monte Carlo simulation? How many simulations do you do? Thumb rule. Until 10 failure points. That is the thumb rule. Okay. What is the mathematical way of finding it out? You will find the coefficient of variation, and you will decide what is the coefficient of variation you want, and then by assuming binomial trial or binomial distribution, you can find out expression for the coefficient of variation, and from there you can decide what is the number of samples you need, given you know the range of probability of failure you are looking at. In reality, you will not know the range of probability of failure beforehand. So you will be doing it simultaneously. You will calculate PF simultaneously, and after, let's say, each 1000 iterations, you will calculate this coefficient of variation for that PF, and it will continue until convergence. In practice, you will not know the range of PF. So in that case, PF is known, N is known. So you cannot use that formula. So what you will do is that you will keep on estimating PF, and as PF evolves, you keep on calculating this coefficient of, that number of samples, okay, or the coefficient of variation also. And when the COB goes towards or below the threshold, you stop. Okay, so that was what we discussed in Monte Carlo simulation, 3 lectures before today's lecture, right? What is the other sampling method we have discussed? Importance sampling. The second thing we have discussed is importance sampling, and in importance sampling, we saw that I equal to 1 to n, indicator function xi or maybe I should write x tilde I multiplied by W x tilde I. Any idea why am I writing x tilde instead of x? What is x sample from? X in the first case. From the PDF fxx. Now x in IS is not sample from the same distribution. So because I am not writing the distribution here, so to differentiate between them I am using that sign tilde. Okay. So the sign tilde I am using to denote that x tilde and x do not come from the same distribution. In importance sampling, the samples come from importance sampling density or ISD. Whereas in Monte Carlo simulation, the samples come from the original PDF of the input random variables, right? And this, both of this we have seen. We have seen both of this already. What is the main challenge in IS? What do you think is the main challenge in IS? Finding ISD. I mean, you can find it out, but you don't know if that is the best ISD or not, because the best ISD you cannot use. And the best ISD you cannot use because that is the function of the PF itself, and PF itself you will not know. So you cannot use, right? So here the challenge is finding ISD, which is the important sampling density. Okay. So now, today we are going to talk about, or rather discuss, a third type of sampling method known as the subset simulation. Subset simulation. And this subset simulation was developed particularly for rare event scenarios. So today we are going to talk about a simulation technique known as the subset simulation, which was developed particularly for rare event simulation. Okay. So another sampling technique is subset simulation. Okay, or as it is popularly called SS, and this is particularly useful for rare events. Okay, this is particularly useful for rare event probability or rare event. Okay. So what is this subset simulation? How does it work? What is the principle? We'll start discussing it in today's lecture. I will not be able to complete subset simulation today, but we will complete it tomorrow. 2 lectures would be good enough. If not, then Monday, but definitely by Monday. Okay. So, okay. So, subset simulation. Okay. So remind me, what is the main goal or main objective of reliability analysis? Probability of failure, right? And so the main goal of reliability analysis is probability of failure computing or computation, right? Now this probability of failure is a probability. It lies between 0 and 1, right? And potentially that number can be very, very small. If we can imagine the probability of failure as product of multiple events, or rather as product of multiple probabilities, what do you think, what can you say about that probability? So suppose probability of failure, right? This is what I want to compute. If I can imagine it or decompose it, how I will come to that later, but let's just assume I can, as probability of F1, probability of F2, probability of Fk. Okay. Suppose I can do it like this. Okay. I don't want to use F because later it will create confusion, so I will use F hat. Okay, to avoid confusion. So suppose the probability of failure that I am interested in, somehow, I don't know how, somehow I can represent it in this form. Okay. What can you tell me about this as opposed to PF? They will be larger, smaller, equal. PF1 hat will be smaller. PF1, PF2, all of this will be greater than PF because it is between 0 and 1. Potentially, if the actual probability of failure is, let's say, 10 to the power minus 4, each of these can be 0.1 and you might have thousands of those, right? So in that case, instead of finding out a probability of failure, which is 10 to the power minus 4, which by my thumb rule, I know that I will require 10 to the power 5 simulations. I have to calculate now a very few of those, and each of those will require much less samples. 0.1 means what? 100 samples, right? 100 samples in that case. And this can be done parallelly, obviously. You can think of them parallelly. Actually, you cannot do it parallelly, but let's assume you can do it parallelly. But the idea is that you will never have to compute a rare event. You can bypass computing a rare event by computing significant probabilities and doing a product of those. This big idea is clear. So if you can decompose the failure event into multiple events such that the failure event is product of those events, then instead of computing a rare event which may go 10 to the power minus 7, minus 8, minus 20, I don't know, you will be computing multiple, not one, but multiple event probability of events, but those probabilities are now significant. 0.1, 0.2, something in that way. How that will decompose it, that's coming later. How you can achieve that, is that the question? Intuition is not supposed to come. I have not even talked about intuition yet. But is this intuition coming that this probabilities will be larger than that PF? That intuition is coming. That is the objective for now. How this will happen, I have not even talked about it. So you are jumping the ship, right? So that anyways will come, and that will come just now. Okay. So the next question is that how will you divide it into this kind of event? How can you potentially divide a failure event into such F1, F2, Fk hat events such that each of those will be having significant probability? That's the intuition you were talking about, right? So let us see how you can do that, okay? And that is one of the reasons you will realize why I wrote that hat. So suppose we select events, not hat, but F1, F2, F3, such that, okay? So this is the intuition, right? So in SS, we select events F1, F2, Fk such that F1 is a superset, or F2, which is the superset of F3, is a superset of Fk. Okay. Again, the question will come, how will I define this? So any idea how I can define this F1, F2, F3? Can you think and tell me some way of defining these events for reliability? No. How will you define these events? There is no probability here. I am saying how will you define these events? What is P of F? P of F, what does it define? Probability of failure, which is probability that the limit state function will be violated. Correct? And limit state function is gx less than equal to 0, which can be thought of as g at x less than equal to b. Where, I mean, you can have a threshold also, right? Instead of taking the threshold to the left hand side, you can imagine it as g hat x less than equal to b. You can do that. That you understand? Everyone follows? I will write it once. So failure is defined as or defined by g of x less than equal to 0, right, or less than 0, right? This is this not equivalent to g hat of x less than say b? I can do that, right? Where you can imagine that gx will be equal to what? G hat x plus b. Clear? So then, what is my failure event? My failure event is that g at x is less than b. Correct? Now, if I have to define a f1, how do you think I can define a f1? By changing b. If I change b, then the probability of failure will change, and that will be a different event. So I can always define new events by changing this threshold b. Correct? For example, in a Gaussian, let's say what is the probability that standard Gaussian, what is the probability that the standard Gaussian will be less than equal to 0? 0.5. What is the probability that the standard Gaussian will be less than equal to 1? Greater than 0.5. What is the probability that the standard Gaussian will be less than equal to minus 0.1? Less than 0.5. What am I changing? What did I change in all of this? Just the threshold. So ideally, you can imagine this, hopefully, that you will be able to define these events somehow by changing this threshold. Not somehow, by changing these thresholds. Okay. Now, what have I written here? That F1 is a superset of F2. Correct? F2 is a superset of F3. And the last one is Fk. Fk is your failure event. So Fk, this corresponds to P of F. So that basically this corresponds to g of x less than 0 or g hat of x less than b. Clear? Now in this setup, can you tell me what is probability of F1 intersection F2? What will be it equal to? Probability of F2. Everyone follows? Because it's a subset, intersection means what is the common area? F2 is the common area. Correct? It's like a CDF. It's a CDF, you can think of it like that, but right now I'm talking about probability. CDF gives you probability, but thinking it like a CDF is narrowing down your imagination. It need not be a CDF, it's a probability. Okay. All of you agree? This is equal to probability of F2. Right? What is probability of F1 intersection F2 intersection Fk? What will be it equal to? Pf, because it will be equal to probability of Fk, which is equal to Pf. So this is equal to probability of F. Is this not what I want to find out? This is exactly what I want to compute, right? So what will I do now? P of F is equal to probability of intersection I equal to 1 to k. I'm writing it mathematically. Fi, right? Correct? One thing I just noticed. So previously I was denoting k as number of random variables. In this case, it is number of subsets. So maybe I should use a different notation just to be consistent. So I'm changing k to something else. I don't know what, but that will decide. So k I am changing to m, maybe m is fine, I guess. Why did I remove this? This f is fine, right? M, and one more m here. Okay, so I did it so that you do not confuse when you are reading, let's say, form and after that importance sampling and after that this. So you should not get confused. So because of that. Okay. Now, this joint distribution, how can I write it? Using the product law, right? What is the product law? The product law is probability of F1 multiplied by probability of F2 given F1 multiplied by probability of F3 given F2 and F1 dot dot dot, the last term is probability of Fk and Fm given F1 to m minus 1. Simple product law probability, right? Now, the first term is fine, I don't care. Second term is also fine, I don't want to discuss that. Let's go to third term. What is the third term? F3 given F2 comma F1. Can you tell me in a sentence what does it mean? Both have occurred. Now, what is the probability of F2 and F1 both occurring? It is only F2. So, given F2, F1 is conditionally independent of F3 because of the superset or whatever I have taken, right? So, that means this term I need not write. So, F3 will be given F2 and this term will be equal to F m minus 1, right? So, what have I done here? What I have done is that I have decomposed the probability of failure into probability of events, and you can now understand because of the assumption how that F1, F2 will come. Now the intuition is coming. Okay, so this is the intuition. That was to stage this, set the stage that why we should do it. Any doubt on this one? Because this is the perhaps one of the most important thing of subset simulation. Any doubt? You cannot. F2 given F1 is not equal to F2. Because F2 given F1 is equal to F2 intersection F1 by P of F1. F2 intersection F1 will become F2. So it will become probability of F2 by probability of F1. So you cannot reduce it. You can start cancelling it out, but then you will end up with the what you don't want to compute. So you will not, will not like to do that. Okay. Clear? Any doubt on this decomposition? Now, any idea what this is essentially saying? Can you relate it with some concept you might be aware of? I'm not saying everyone is aware of that. If you're not aware of that, that is fine. But I'm hoping some of you are at least aware of this terminology. So let's see. This reminds you of something? Markov. This is like a Markov decision process. What is a Markov assumption? That the next event or the current event is dependent on the previous event. And this is not just any Markov, this is the first order Markovian assumption. I mean, we are not assuming it, we are getting it. But it's the first order Markovian. That is, F1 will influence F2, F2 will influence F3, and so on and so forth. And because it is Markovian, you can assume at some point Markov chain will come into picture. It will not come into picture today, but it will come into picture eventually, and that you can hopefully appreciate that because there is Markovian, we will use something related to Markovian. Okay, so this decomposition is the basic premise for using subset simulation. Okay, okay. So now if that is okay, let us move ahead. Now who is deciding this F1, F2 and F3? We are deciding, right? And we are deciding it by changing the threshold, B, the B term, right? So can we not select the threshold in such a way such that all but the last one becomes equal? The last one I cannot do anything because Fk is my original threshold. That I cannot play with. The other thresholds, 1 to k minus 1, I can play with that. So I should be able to play with that in such a way such that all of these thresholds become, all of these probabilities except the last one become equal. How do you find out these probabilities? By changing, how do you find out this F1 and F2? By changing this threshold beta or B. And this threshold B, who is changing? I am changing. Correct? So I will decide what is my F1, what is my F2 and all of those things. So I have that power to select a B which will ensure that probability of F1 is equal to probability of F2 given F1 is equal to probability of F3 given F2 is equal to probability of Fm minus 1 given m minus 2. Probability of Fm, I cannot do anything, that threshold is fixed. Because that's my original target. Are you able to appreciate this? Right? So if you can do that, what will be my result in that case? So considering we set the threshold, obviously, or to be more specific, I should say select Fi's such that probability of F1 is approximately equal to F2 given F1 is approximately equal to probability of Fm minus 1 given Fm minus 2. I am saying approximately because you are setting a threshold, you have to decide until what decimal place you will go and all of those things. So that's why this approximation side, because for numerical precision or whatever you call it. And you will see that this approximation will also come when I talk about the algorithm, which I'll do today. Okay. And let's say that is equal to P naught. Okay. So then what is my PF? What will be my PF? P naught to the power m minus 1 multiplied by, because the last one I have not done anything. So that last one I need to calculate. Multiplied by NF by N. NF by N is the probability of Fm given Fm minus 1. Okay. So NF is calculating number of failure in the last conditional probability, and N is the number of samples for each of this level. This N number will keep fixed for computing each of this. So N here is number of samples at each level, and you can understand that will keep same, and this is equal to number of failures for probability of Fm given Fm minus 1. Okay. This is clear. Now remember, I am saying the number of samples I am going to keep fixed. I'm going to fix it, right? Which means the number of decomposition should be selected in such a manner so that this nf by n should be of the same order as P naught. Otherwise, you cannot keep the number of samples same. And you have to also keep in mind this is a product. If one of these goes to 0, everything goes to 0, which means this number n has to be selected in such a manner so that all of those are non-zeros. And obviously for others you are fine because it's P naught, but you have to keep in mind this nf by n should be of simpler order. For example, suppose my probability of failure is 10 to the power minus 5, right? I cannot do 0.1 multiplied by 0.1 is 10 to the power minus 2 multiplied by 10 to the power minus 3. If I do that, my n will be wrong. Either I will be using too much n or too few n. If my probability of failure is 10 to the power minus 5, it should be 5 levels. 0.1, 0.1, 0.1, 0.1, 0.1. Then you know that for each of this you need n, and that n will be 100 or whatever. Repeat.
We get more number of NFs.
So I said same order, right? When I say same order, what does it mean? If you are getting more in the last one, right? So then you should decompose it once more. You should decompose it once more. Otherwise, you are using more samples in the other cases. So it's the balance you are looking at, right? You want to use the optimal number of n. That's the ultimate goal, to reduce the variance, to increase the convergence rate, to reduce the sample requirement, and all of that. Okay. Any question? Threshold you can always choose, and threshold is not important, but threshold you will generally fix at a number. But how many of this decomposition you are doing, that will be what you will be selecting, and in fact that will be automating. You will not do that. I think when I write the algorithm next, you will realize that you don't need to do that. Okay, but on a theoretical basis, you should be clear that this has to be of the same kind of order. Okay, this P naught value, what is the P naught value you should take for the algorithm is the open question. Standard values for P naught is 0.1 or 0.2. People have seen that with that it kind of converges. 0.1 or 0.2. Okay, those are very standard numbers that are used in subset simulation. Okay. So yeah, PA and all of these things. So now let us look at the algorithm. How will you use it in practice? Okay. The algorithm will be incomplete because you will realize that some of the things we cannot compute, and those things obviously we'll talk tomorrow. Okay. So algorithm. What are the inputs, do you think, to this? What are the inputs? P naught. Threshold is not an input. These B's will come out automatically. So B's are not an input. Okay. Anything else? Now, number of decomposition will also come out automatically. That will also not be an input. Fxx, the PDF has to be the input, the one from which you want to sample. And n. These three are your inputs. Okay. Now, what will you do? Step 1, sample x from fxx. So basically we will sample xi from fxx, and for I equal to not for all, for I equal to 1 to n. So basically you will sample n times. You will generate n samples of the input random variable.
When we say sample from our do we have any stochastic simulator for that?
Okay, stochastic simulator and sampling are two separate things. You can sample a stochastic simulator. That's a different story. So let me start with sampling. That part I did not cover. Intentionally I did not cover. So sampling, true random sample you cannot sample. There is no method existing right now that can actually sample or that can generate samples that are random in the truest sense. The only thing I am personally aware of is that wind speed, if you use wind speed and measure it, and based on that you might get something random. So what we actually generate is quasi-random samples. And how do you generate it? Basically try to uniformly fill the space randomly, and that will give you quasi-random or rather pseudo-random actually. Sorry, not quasi. Quasi is different. Pseudo-random. Quasi is also there, but this is pseudo. So you will generate pseudo-random uniform random variable. And that you can generate because uniform means it should be equal, right? More or less uniform. Okay. One scheme that I'm not very sure, but I've heard people use is the clock time, date and calendar and time, because that is something that is never repeated. So that means you are using a separate different thing to generate samples every time. So it becomes kind of random. But again, there is a pattern. The date and time is actually not random. So that's why these are pseudo random and not truly random. Okay. This will allow you to generate random samples which are uniform. And then you do inverse CDF to transform those to any standard PDF you want. You will do an inverse CDF of Gaussian. Over the uniform, you will get Gaussian samples. But remember, those are pseudo random numbers. And that is known as sampling. You talked about sampling stochastic simulator. So let's say I have a simulator F, not F, G. So I will call G as a stochastic simulator if for each run of the simulator I start getting different results for the same X. This will only happen when this G is function of X and zeta, where zeta is some random variable. So now sampling stochastic simulator means you will sample this zeta and run this simulator for a given X. So imagine X plus zeta, that's a stochastic thing, right? You sample X, you keep X fixed, zeta you sample, you run it. You will get Z of G and that will change. So that's what is known as sampling the stochastic simulator. Okay. But the first part the second part I could have avoided answering now, I could have answered him separately. First part I intentionally answered because in all of this there is an inherent assumption that you are able to sample. Right? And you will be using, when you write code, you will be using numpy.random.rand.randn, and you will be allowed to use that in sampling. Like in the Monte Carlo simulation question in homework 2, you are allowed to use those things for sampling. Okay. So you will be using those, but what is happening under the hood is what I just explained. Okay. Okay. So you will sample 1000 samples from the PDF, right? And for each of these samples, the next step is you will evaluate the limit state function. Evaluate limit state. Okay. Evaluate the limit state function. Okay. Which is yi is equal to g of xi. Right? G is your limit state function. You have I samples. For each of the samples, you put it into a limit set. It will give you yi. Okay. And this is again for I equal to 1 to n. Okay. Step 3. And now, I mean, there is nothing new until step 2, to be very honest. This anyways you have done even for MCS, right? Even for importance sampling, we are doing something similar. Step 3 is new. Step 3, what you do is you arrange these yi's in ascending order. Okay. Arrange or sort. I will say sort yi is in ascending order. What does sorting it in ascending order means? That the upper values will be the failure points, the lower ones will be the safe points, assuming there is some failure points. Because if you ascending order, the negative ones will come first, which is less than 0, which denotes failure. The positive ones will come later, which are the safe points, and you are fine. Okay. Now, remember, I need to select a threshold, right? And I need to select a threshold such that my failure should be equal to failure probability of the first level. P of F1 should be equal to P naught, say 0.1. How do you think I will select the threshold now? I have arranged it. What should I do next to find out the threshold? I want 20% of my samples to fail. So I will select a threshold such that only 20% fails. So if I have 100 samples, I will take the first 20 samples, the last one will be my failure. Clear? So the threshold is selected by us arranging it. So simple, I will tell you once again. So suppose I have arranged y, right? Y arranged. This is equal to minus 100, minus 98.9, minus 7.6, dot, 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 let's say minus, I don't know, 0.01, 0, 0.89, and then it is continuous, right? And now I want, let's say, 3 samples to fail. Just as an example, if I want 3 samples to fail out of, let's say, this 10 samples, then my threshold should be this one. If that I set as my threshold, that means first 3 are failing, everything else is safe, and my P naught will automatically be equal to 0.3 in this case, 10 out of 3, right? In your case, it will be 0.1 or 0.2. You will have hundreds or thousands of thousand samples, and will do that. But this is what you will do. Everybody follows. So sort it in ascending order, and then select threshold such that P naught holds.
Is limit state function g of xi. So g of xi normally we take less than 0 values as all the failure points.
Correct.
Why we are just basically taking that part of the
What is your failure point here in this F? What corresponds? What? No, F, left hand side. Which of this F corresponds to failure? Fm. So that should be 0. F1, should that be 0? This is F1 I am computing now. What I computed just now is P of F1. I did not compute P of F yet. So can't F1 be an event where the threshold is negative? Is that not possible? Can't F1 be an event where Gx less than equal to minus 0.6 denotes F1? F1 is not failure. F1 is not failure. Is F1 failure here? What is the problem with minus? Less than 0 for which one? Less than 0 for Fm. Do you think even for F1 it should be less than 0? And F1 should be equal to Fm. But then is this superset condition satisfying? Is it getting satisfied in that case? Then now I showed the example of negative. It can be positive also if you take your limit set to be greater than 0. That not limit set, failure domain to be. It's on you how you define the limit state. It has nothing to do with negative or positive. It has everything to do with how we will define F1 and F2 and Fm. And Fm will be your actual threshold. And that actual threshold, generally we set it to be 0 because the actual threshold we take to the left hand side. Remember, actual threshold is actually not 0. Actual threshold is what? Remember the cantilever problem. The threshold was L by 325. That is the actual threshold. What we do is that for our convenience, we said, okay, L by 225, 325, take it to the other side. And L by 325 minus PL cube by 3i is my limit state. But ideally, it is PL cube by 3i is equal, is less than equal to whatever, right? Or greater than equal to in this case. So keep that in mind. Okay.
The example that you gave, how we set F1 to be a superset.
I have not even finished it. So it is coming next. But you can easily understand how it will be. I have done it. What do you think will be the threshold for F2? This is F1 right now. 7 minus 7.6 is the threshold of. The next one will be F2 will be what?
Above.
So then it will keep going there. So you can imagine like that. But it will not work like that. It does not work like that. So I'm coming to that, how it will work. Okay. Any doubt? Okay. Okay. So this is one example I gave just to tell you that how will you select? These numbers are imaginary. I came up with this number. These numbers can be positive or it can be negative. Does not matter. Okay. What I came up with is that I'm going to arrange it and select the point such that the failure is 3 out of 10 in this case. So I have taken 10 samples and I'm saying only 3 will fail. Your confusion is coming because in real case, this is actually increasing the probability of failure. In reality, what will happen is that your failure points will end much before you cut the threshold. In real point, what will happen? You will have 10 to the minus failure probability, I want 0.2. So actually your failure will end and then you will take the threshold. Correct. But I wanted to explain the 0.3 part, right? Usually what will happen? You are looking at 10 to the minus 5 and you are trying to decompose it into 0.2 times 0.2 times 0.2. So 0.2 is greater than 10 to the minus 5. So that means your threshold will be on the much before it will fail. And that is creating confusion. But this is not a real example. This is to show that we will take only the first 3. Because in this case, your actual failure probability is 7 out of 10. I am decomposing into 3 out of 10. I can never get 7 by 10 by multiplying 3 by 10 into 3 by 10 into 3 by 10. This is just to show what you will do. You will arrange it and select the P0 times n samples. That is what it means. Okay. So, yeah. Okay. The subset part is clear. What will happen? Okay, but the subset part is not yet there. Subset again, you will not select that. It will come out automatically. So select threshold such that P0 holds, which is equivalent to n times P0 failure points, right? Points, which is equivalent to n times P0 is the index at which you will set the threshold. This is what it means. Like it was 3 because 0.3 times 10. So n times P naught is the index in that array that you will select. It's the correct. So that's why I use the approximate sign. You remember I use the approximate sign. So you will take the nearest one in that case. So that's why at that stage only I started with the approximation sign. So you will try to make it 0.2. It might not be. It might be the next sample that you're taking, and then in that case it will be 0.21 or something like that, which is fine. Okay. Okay, this is clear. Now step 5 onwards you will not understand because that is for the next lecture. This is where I wanted to end, but I'll tell you what will happen after that. Step 5 we will start with, because now step 4 was easy because it was P of F1 and we know how to compute P of F1. Step 5 will be computing P of F2 given F1. So that's a conditional probability, and we have not discussed how to work with conditional probability. So step 5 actually what you will do is that you will start with failure points in step 4 as seed. Seed means initial samples. Seed does not mean the seed number that you use when using sampling. Okay, as seed, and use Markov chain to sample n samples from probability of F2 given F1. Clear? What will do? Obviously it is not clear what is Markov chain, but on a higher level you can understand what I am trying to do, but what we will try to do in the next lecture. We will try to now in the next step 5 try to sample from the conditionals P of F2 given F1 or Fi given Fi minus 1, and because it is conditional we have to use the Markov chain, and for Markov chain we will start with the initial seeds or initial samples of the failure point from previously, because it's a subset of the previous one, right? And this will continue for k minus 2 times, because one time you have already done, and another k minus 2 times. Each time you will get P naught, P naught, P naught. The last one you have to again do Markov chain, but you will get NF by n, and then you will do the product, and that will give you your probability of failure. Okay. So the key element here is that how to sample from conditional distribution. If you can sample from conditional distribution, you are in a position to use where is the formula? That one, the bottom one. To use that P naught to the power m minus 1 multiplied by nf by n to compute the probability of failure. Assuming you can sample from the conditionals. So tomorrow we will see how you can use Markov chain to sample from the conditionals, or in general how you can use Metropolis algorithm or Metropolis Hastings algorithm to sample. Okay. Okay. Thank you.